All right, we're working pathways 3.11, compute molar masses in grams for different compounds. Now, turns out that this type of problem is super important for this chapter and your continued progress in the chemistry class, okay? It's not too terribly difficult to address this type of problem. We simply add up or sum up the parts that make up the molecule, and that gives us our molar mass, okay? But we need to have the ability to compute the mass in grams of a mole of any compound that I give you. So let's practice this, just jumping right in. We start with this first molecule, N2O4. We see that 1 mole of this dinitrogen tetroxide, right, has 2 moles of nitrogen atoms and 4 moles of oxygen atoms. This is what's required to make 1 mole of this. It's the ingredients. So to compute the molar mass, we simply sum up the parts, right? We're going to add the oxygen contribution to the nitrogen contribution. Since there are 2 elements involved, I need 2 moles of nitrogen. If I look at the periodic table and track down what the molar mass of nitrogen is, it's 14.01 grams per mole. If I look at the periodic table and I track down what the molar mass of oxygen is, your book says it's 16.00 grams per mole, and I've got 4 moles of atoms. So that's the math that I need to carry out. Okay, so you sum the nitrogen contribution, get a little bit over 28, and then you add that to the oxygen contribution, so it's around 64. And then you sum those 2 numbers together and get 92.02 grams per mole. So if I have exactly 92.02 grams of this molecule, I've got 1 mole of it, okay? That's my molar mass. Practice again. This molecule. This molecule, this OH group, really sticks out to me. Because when I see that in an organic molecule, it oftentimes signifies something that I've got called an alcohol. It's an alcohol function group, okay? This molecule is butanol. If you've ever heard of butanol, that's what this molecule is. We can compute the molar mass of this stuff by adding up the parts. Now we ask ourselves, okay, what parts do I have? Well, for every 1 mole of this, I've got 4 moles of carbon atoms. Looks like I've got 10 moles of hydrogen atoms, and I've got 1 mole of oxygen atoms. So those are the parts that go into it. Now notice that I just added these hydrogens together. There's nothing wrong with that. They're all hydrogen, okay? So I've got these parts. Now I can figure out, what are the masses of each, okay? So if I look at my periodic table again, I see that the entry for carbon is 12.01 on your textbook. I got 10 copies of hydrogen, and if I look at the entry in your textbook for hydrogen, I get 1.008 for its molar mass. And then of course I have to add 1 copy of oxygen in here on the end. It's got a molar mass of 16. So 1 times 16, I'll just write the 16. All right, everybody see where I got those numbers from? Again, it's from your textbook's periodic table. So now I'm going to add the parts together. And if I do so, my molar mass for the butanol is 74.12 grams per mole. If I've got 74.12 grams of butanol, I've got exactly 1 mole of butanol. That would also correspond, of course, to Avogadro's number of molecules of butanol, 6.02, 3 times 10 to the 23rd molecules of butanol in this many grams. Okay, so you can start to see how we can interconvert between grams, moles, and molecules of a compound. That is a crucial skill for Chapter 3 of your textbook. Okay, So moving on, let's try this ionic compound. It's a hydrate, right? Magnesium sulfate heptahydrate. Magnesium sulfate heptahydrate. Got to add up the parts, just like we did before for the molar mass. So MM molar mass is equal to a bunch of things added together. All right, so it gets a little bit more complicated here because we got lots of different elements involved and different numbers of elements. But one thing I know is that there's 1 mole of magnesium per mole of this stuff, okay? So what I can do then is I can add in magnesium's contribution. Now, if I look at your periodic table, in the textbook, that's 24.31 grams per mole. And since I've got 1 of them, I only add that in once, right? Now, similarly, when I look at that formula, the next element I come across is what? Sulfur, right? Sulfur. I've got 1 mole of sulfur atoms per mole of this compound. So the sulfur contribution is 32.06. That's just the number that's on the periodic table. Sulfur. All right, so I've got 2 elements remaining, oxygen and hydrogen. I've got to consider each one independently. So the next question then is, for every 1 mole of this compound, how many moles of oxygen atoms are present? For 1 mole of this compound, magnesium sulfate heptahydrate, how many moles of oxygen atoms are present? This is a little bit confusing perhaps, okay? Because there are 2 different sources. We have some oxygen from the sulfate, polyatomic ion. We have some oxygen from the water that's making up the hydrate. We just combine these basically, okay? Doesn't matter what part of the compound they're from, we're just adding them together, adding all the parts. So I've got 4 moles of oxygen atoms here per mole of compound plus 7. So in total, I've got 11 copies of oxygen at 16 grams per mole. And I see where I got the 11, 4 in the subscript, and I'm adding that to the 7 oxygens from the 7 copies of water, because the 7 out front tells me I've got 7 copies of water per formula unit. That's 7 oxygen atoms plus the 4 here. So that's 11 total, right? So if you're having a difficult time seeing that, you may want to take a few minutes to kind of review, okay? But indeed, I need to do 11 times 16, where 16 is the molar mass for oxygen. Unfortunately, I'm running out of space here in my line. I'm going to have to erase this for a second, just so I can continue this problem, and then we'll erase what I do and work this last one, okay? But I've got one more element to consider, my hydrogen. Now, if I look the number on the periodic table, I get 1.008 for hydrogen. That's for a mole of hydrogen atoms, but how many moles of hydrogen atoms are required to make 1 mole of this? Well, let's look. It looks like the only source of hydrogen is here in the hydrate, in the water molecules. And I've got 7 water molecules per formula unit of this, or per mole of this. Okay, well, per mole of this. 7 water molecules per mole. This was 7. There's 7 moles of water molecules per mole of this, right? Now, the thing is each water molecule has what? 2 atoms of hydrogen. So can you see that in reality, I've got 14 atoms of hydrogen per formula unit of the hydrate. And I've got 14 moles of hydrogen atoms per mole of the magnesium sulfate heptahydrate. So I need to multiply hydrogen's number from the periodic table by 14. Okay? So hopefully you followed along with all that, because that is sort of an important thing. So what we need to do now is we need to add up all these numbers. And if we do, we get a number a little over 246. It looks like it's 246.482 grams per mole. That's the molar mass of magnesium sulfate heptahydrate. Again, the tricky thing there was counting the number of atoms that you got based on your formula, right? Remember, when you're computing the molar mass, you want to know how much does the mass of this substance weigh. 1 mole of it, how much does it weigh in grams, right? You gotta add up all the parts, not only for the ionic compound, but if it's a hydrate, you gotta add the waters in as well. And you gotta be really, really careful about making sure that you're counting the right number of atoms of each type. Okay, that's absolutely crucial. So this is a nice example for that. Okay, so now that we've seen that worked, I'm gonna go ahead and erase it so we can work this last one, okay? We have space. All right, so this last one. I'm going to compute the molar mass of this calcium salt. This is calcium acetate. Remember, acetate is one of our polyatomic ions from the periodic table, okay? So for every 1 mole of that, what do we have? Well, it looks like we've got 1 mole of calcium. And calcium's entry in the periodic table is 40.08 grams per mole. So I've got 1 mole of that. I've got to add calcium's contribution to the 3 other elements. So let's start with carbon then, okay? Start with carbon. So let me ask you this. How many moles of carbon atoms are present in 1 mole of calcium acetate? Be careful, right? I would argue it's 4. Because for every 1 mole of this compound, I've got 2 copies of my acetate. That's what that 2 tells me. 2 copies of my acetate. And for every 1 copy of acetate, I've got 2 carbon atoms. So because I've got 2 copies of acetate, I've got 4 carbon atoms in a formula unit of this stuff, okay? So I need to add 4 times carbon's contribution of 12.01. Now I'm running out of space here, so I'm going to hit ... and I'm going to continue this computation down here, okay? So I'm going to add other terms, right? Because we're not done yet. We still got to add hydrogen and oxygen contribution. Now, how many moles of hydrogen atoms per mole of this compound? Looks like it's 6. And since the value on the periodic table is 1.008 for hydrogen, I'm going to multiply 6 by that value. And I'm going to add 1 more number in then, the oxygen contribution. Which is 16 times 4. There are 4 oxygen atoms per formula unit, or 4 moles of oxygen atoms per 1 mole of calcium acetate. And each mole of oxygen atoms has a mass of 16 grams. That's from the periodic table, okay? So again, we're adding all our parts together. But the trick is realizing which parts are present, okay? Now, if you have this all together, looks like we're going to get a value a little over 158. 158.168 grams per mole for calcium acetate. So if you go in lab and you weigh out that amount of calcium acetate, you've got exactly 1 mole of calcium acetate formula units, right? So this is computing molar mass. It's pretty straightforward. You just add the parts from the periodic table. I think the most difficult part of this is just figuring out how many copies of each of the elements that you need to add together to the total. If you can master that, you're good to go.